just a minute. All right, so I think we're going to get started. You want to do an introduction?
Yeah.
And I'll hand you the microphone.
Oh, okay. Cool.
And this is the one that's actually going to go out. So.
Oh, okay, awesome.
Right?
Well, hi everyone. Thanks for coming out today. We're excited to have this joint event with Chicago R user group. My name's Olivia. I'm from PyData Chicago, and then this is So Chang, our co-organizer, and then Justin from Chicago R user group. And we would just like to thank our major sponsor, NumFOCUS. NumFOCUS is a nonprofit organization that supports and promotes development and adoption of open source scientific software. Many well-known Python libraries are supported and maintained by NumFOCUS. It provides funding and community support to software including, but not limited to, Jupyter, Pandas, Matplotlib, NumPy, SciPy, Julia, and Dask. In turn, NumFOCUS is supported by several large companies, including IBM, Microsoft, and Intel. Yeah, and we are recording this talk, so anyone who wants to share it in the future, you can do that. Yeah, and then I'm really pleased to introduce Brian Peterson. And I'll just read a quick intro about you. So Brian is a quant, an educator, and an entrepreneur, and an open source advocate. He is on the graduate faculty of financial engineering at the University of Illinois, where he teaches about the design and analysis of automated trading systems. Brian is also an entrepreneur who manages multiple firms, mostly but not exclusively in the financial services arena, where he works as a quantitative analyst. Brian is also the author and co-author of more than 10 top source packages for using R in finance, the longtime co-administrator for R in languages, participation in the annual Google Summer of Code and Open Source program, and a founder and member of the committee for the annual R Finance Open Source Finance Conference held at UIC in Chicago. Okay, so I'll hand it over to Justin if you want to say anything about Chicago R.
Okay. Hello, everybody. Thanks for coming. My name is Justin Shea. I help organize the Chicago R user group. I'm also a faculty member here at Roosevelt University, hence our space, where I direct the finance honors track, where I teach students how to use R. I hope to include some Python in the future here, but for now, it's just R to do our statistical analysis and backtesting. And so, as Olivia mentioned, we've got our R in Finance conference coming up May 19th and 20th. That's at UIC. And so I think we got about 30, 35 talks.
Mm-hmm. Some of them are even Python.
Some of them are Python. Su Cheng, for example, other PyData organizer, lead organizer here, is going to be speaking there. And so if you kind of like the material that's being presented today, it'll be this sort of level of rigor for many of the talks. Although this one's probably more in the upper tier of the rigor. But anyways, thank you all for coming. And I'm going to turn it over to Brian now.
Well, thank you all for having me. So I want to say a little bit first about how this topic, actually, first I'll say, I write both Python and R and several other languages as well. We tend to use R for statistical analysis, and that shouldn't be surprising to anyone because R was originally created as an S-like language, and S was the language that was created for statistics at AT&T Bell Labs. So I write Python code every single day, but usually just for gluing other stuff together. I use it for moving data around. I use it for transforming data. I occasionally use it for certain machine learning models. But generally speaking, when I need to do statistics, I use a language that was designed from the ground up for doing statistics. So one of the things we'll see here is I'll reference Python packages and Python ways of doing things where I can in this talk. But because design of experiments is a field of statistics, you shouldn't be surprised that there's far more design of experiments in a statistics language than there is in Python. So again, I use Python every day, but when we're doing statistics, we usually use R. So I'll say something else. I started working on this particular topic maybe as much as a decade ago, where I started thinking about design of experiments and how it would fit into what I do every day, which is quantitative finance. I didn't get very far though, because there's basically, you can count on one hand the number of papers that rigorously use design of experiments in finance. There's almost nothing out there, and none of them are good. They're all horrible. In fact, we replicated them, they didn't work, they had bad methodologies, and it just wasn't useful to us. So last summer, I took my family on vacation. I came home with the one souvenir I didn't want. I came home with COVID. And got brain fog for a few days. I'm vaccinated, my family's vaccinated. I never felt I was in danger, but I simply couldn't think for 4 or 5 days. And I realized I was doing better when I wanted to do math again and write code again. And I realized that I didn't have to be back in the office for about a week. And so this is very rare for me to have a week when nobody is going to bother me and when I can actually think hard thoughts. So the genesis of most of this work was in a week last summer when I could actually synthesize a bunch of stuff I've been thinking about for a very long time, and start putting it all together and applying it specifically to quantitative finance. So the examples that we're going to talk about in this talk are from quantitative finance. Well, come on. Only if it lets me change slides. Yeah, that should work, but it's not. I tried that too. That's why. It signed me out. There we go. That works. Okay. So, whoops. Why did we hit that? It is a Mac. That's the problem. All right. Cool. There we go. You're sharing screen. Yeah, I am sharing the screen. So, okay, sorry about that. So it had logged me out between when I was teaching and when I came up here. So, anyway, so design of experiments was a field that was started over 100 years ago by statistician R.A. Fisher. So you've heard his name in kind of any statistics tests. You find his statistics all over the place. Design of experiments is widely applied in fields like agriculture, psychology studies, pharmaceutical research, manufacturing, chemical engineering. As I said earlier, it's not widely applied in quantitative finance, where I spend most of my time. So for those of you who are in some of those other fields, you can find tons and tons of research on design of experiments. And I strongly recommend that you go look for some of this research because it'll save you a ton of effort, especially computational effort. So for today's talk, we're going to focus mostly on computation and on how this fits into computational experiments as opposed to physical experiments. If we have time at the end, I'll talk more about some of the areas of design of experiments that apply to physical experiments. But many of the things that were designed 100 years ago, not surprisingly, for physical experiments don't apply as much in computational experiments. And since we're here at a data science meetup, I assume that lots of you are dealing with computational experiments rather than physical experiments. So one of the problems of approaching design of experiments is that it's really filled with kind of difficult terminology. I'm sorry, Justin, I didn't think that I should use a white background and a dark, dark text. So you know, there's often the words themselves in design of experiments aren't difficult at all. but they're drawn from the fields of research where they were originally employed. So we have things like plots coming out of agriculture, or treatment plans from medical research. We have contrasts from biological sciences. Now, I'm a scientist originally, so I get all this stuff, but it's very hard. It was very hard for me to approach design of experiments because it became very difficult to kind of think about how these things come together. So what I'm going to try to do today is I'm going to try to present these techniques using terminology that may be more common to you from data science and quantitative descriptions, rather than necessarily focusing on the design of experiments descriptions. So why are we doing all this? We're trying to evaluate the cause and effect of our changes on our inputs, methodically test our parameters to evaluate parameter dependencies and overcome noise. And our goal is to overcome biases that assume that data is randomized or independent or normally distributed. So in many cases, many branches of statistics assume independent observations. They assume normality. I can't assume any of those things in my world. In my world, it's almost never true. My data isn't stationary. I have fat-tailed data. I have random data. I have jumps in my data. This is one of the reasons why design of experiments is really important, because it enforces normalization of the parameter research space, and it allows us to more readily examine those IID assumptions or overcome them based on using better experiment designs. It allows us to make better predictions of the effects of our parameter changes. And perhaps most importantly, in a world where we often have, thousands of features and billions of rows of data, it allows us to use less compute to find meaningful answers. One of the biggest problems that we find in large computational studies is things like multiple testing bias, overfitting biases. So we can use smaller sets of tests to actually get more statistically meaningful results. So we use both less compute and get answers faster, and we have less chance of overfitting our data. So that should be interesting to anybody who's ever dealt with really large data sets and thrown a whole bunch of stuff against the wall. So why wouldn't we just test everything? There's often too many combinations, tens of thousands to millions to billions of possible combinations to test. It's too expensive to test in compute, in time, in money, in wasted output. In any non-smooth or nonlinear interaction, multiple testing bias is a huge problem. There are lots of statistical models that are used to adjust for multiple testing bias. And you can often find that if you apply a giant test where you test millions of possibilities or billions of possibilities, what you can find is that you may have no statistical power at all left at that point. So even if your results might be valid, they statistically might be completely invalid. So if you start using things like fixed level designs in design of experiments, which we'll talk about in a bit, the power and precision of your test is actually increased by the product of the levels. So you can do a smaller number of tests and get a more statistically significant test. So the too long don't read about this is that more parsimonious tests can actually have significantly higher power. So why not test things one at a time? Lots of classical approaches to parameter experiments vary one variable at a time. There's two big problems with that. One, it's inefficient, and two, it can't account for parameter interactions. Now, at least in my world, there are almost always parameter interactions, and so we want to really account for those. Additionally, it assumes that you hold constant or fixed all the other parameters, so none of the other parameters vary. So that's why testing one at a time generally doesn't work. So let's start with the idea of a brute force approach, or what's called a full factorial approach. So in this type of model, all combinations are tested. So in R, you do this with the expand grid function, and we're going to use two examples here that we'll come back to in a little bit to explain why we might want to use fewer tests. So we're going to do a 5 things taken 3 at a time, where each parameter has 3 levels, and 5 things taken 5 at a time, where each parameter has 5 levels. In Python, you do this with list comprehensions, where you kind of do, the range for each one and keep going there. The list comprehensions get really complicated, so I don't like doing it that way, but you can do that relatively easily in Python. So at the end of that, what you end up with is these giant lists, these giant tables of combinations for your brute force combination. So your 3-way design has 243 rows. Your 5-way design has 3,000 rows. So that's the total number of brute force combinations here. Now, if you look at this in the columns here, variable 1, 2, 3, 4, 5, you just literally are building every combination. 1, 2, 3, 4, 5 in variable 1 and all 1s and everything else. And then 1, 2, 3, 4, 5 in variable 1 and all 2s in the second variable, and so on and so forth. So you're actually getting all of the possible combinatorial combinations of these parameters. Now, this is a relatively tiny example. This is a very small toy. And so you realize that we're already at 3,000 combinations on this very small toy. So we're going to try a small example. It's a Bollinger Band example. For those of you who aren't in finance, it doesn't really matter what it does. It's a trading strategy that's often used to describe mean reverting or trending models. But the key thing for this purpose is that it has two parameters. It has a standard deviation, which are the bands in a range of 1 to 3, and it has a moving average, which is the midpoint, in a range of 10 to 40. So with a step size of 1, that creates 93 parameter combinations. Not very many parameter combinations at all. And there's no reason not to brute force that small of a set. But for our example, we'll use that to just kind of think about this. So if we do a regression model, we can look at the importance of each of those parameters. And if you look at little stars in here in this table, you'll see that not only both of the parameters are significant in terms of their predictions, but also the combinations of the parameters are significant. The MA parameter and the standard deviation parameter, the combinations of these are also significant. So what we're doing here is we're analyzing the parameter interaction and finding that the interaction of the two is also significant. So in regression terms, in direct regression terms, direct regression effects are typically denoted with an additive model. So Y with respect to A plus B. Interaction effects are denoted with a multiplicative model. So Y with respect to A times B. The parameter importance regression demonstrated the parameters are all significant, both individually and in combination. But how do we understand those interactions? We can examine those interactions too, as things vary. So in this case, what we're doing is we're looking at all the parameter interactions. What you're seeing here on the x-axis is the moving average parameter. The rows are, the lines are each of the standard deviation parameters. Those only varied from 1 to 3, so we have 3 lines here. And then the left-hand column, the y-axis, is different objective functions that again come out of finance: net trading P&L, profit factor, number of trades, average win-loss ratio, which again aren't as important for this if you're not in finance. But what we see here is pretty interesting in that on the top row, we see that the lines cross each other a lot. So that's a visual way of seeing that the parameters are actually interacting with each other. So if the lines never cross, the parameters aren't interacting. So you can see just visually that these parameters have interactions. So even though we already knew that from the regression analysis that we did, we can see it visually here as well. Except for the one on the bottom, where we see that against number of trades, they're clearly significant in that there's a clear pattern. As the moving average parameter goes up, the number of trades goes down, which makes sense because that a moving average parameter is a longer look back period, so there are fewer trades. And as the number of standard deviations goes up, there are fewer trades. The top line is the smallest number of standard deviations, so it's the tightest range of variation. And the bottom line is the largest standard deviation, so it's got the smallest number of trades. But those parameters aren't interacting in that sense. So they're clearly significant because you can see the pattern, but they are also not interacting in that case. And in the final case, the average win-loss ratio, it doesn't look like they're even significant. You know, there's not a clear pattern. It's not sloping up and to the right or down and to the left. But there's clearly some noise interaction in there. So we can see things very quickly by modeling this regression interaction, even though that regression interaction isn't important to what we're trying to find out at the end. So you can also build plots of these. These are called response surface plots. You can do it with any plotting package. You can use 2 parameters and a response variable. You can use a parameter and 2 response variables. You can use a composite coded parameter interaction. They make very pretty 3D plots. We find them completely useless. So we sometimes put them in presentations because they look nice, but I don't find them useful in terms of actually doing any sort of real analysis. But there's a bunch of statistical analysis that you can do with response surfaces as well. But they're really all regression problems. So they're all looking at regression coefficients. So you can get standard regression models to evaluate these interactions. I showed you one a little bit earlier. You can get some additional tools if we use standard coding. We'll talk about that in a little bit. Software packages like RSM and R, SAS has multiple response surface functions. There's a little bit in the PyDoE package in Python for doing response surfaces. But really, what most people are trying to do when they do response surface analysis is they're trying to do optimization. They're trying to actually predict the response based on the changes in individual variables. So getting into design of experiments itself, let's say we got hundreds of thousands or millions of parameters, and we'll show a bigger example in a little bit. We want to test fewer things because it's just too expensive to test hundreds of thousands of things and maybe learn nothing and maybe have low statistical power. So what we'd really like to do is we'd like to do something called the screening design. Our goal is to evaluate our parameter importance, to determine interactions between those critical parameters. If you think things are linear, you can do relatively tiny numbers of parameters. You can have a high and a low value for each parameter if you think the combinations are linear. So now you get 2 to the k combinations where k is the number of parameters. If the parameters are convex or quadratic, you might move to 3 or 5 levels for each parameter. Now you have n to the k combination, where n is the number of levels and k is the number of parameters and n is the number of levels. So in these cases, what you're doing is you're vastly decreasing your total search space in order to get a reasonable coverage of the whole space without having to test everything all at once. So ideally, the whole point of doing this kind of design of experiments approach is that we want to use the most parsimonious design we can to run our experiments. We want to preserve degrees of freedom. For those of you who are used to regression analysis, you can think in degree of freedom terms. How many degrees of freedom are consumed by the analysis? If you run 1 million combinations of all the things, you've used all your degrees of freedom. So the likelihood that you have a statistically valid result is very, very low. So by shrinking the number of tests that we run, we actually increase our statistical likelihood that we haven't overfit and that we still have degrees of freedom. Hopefully it increases insight. It becomes easier to explain and understand a smaller model than it is to understand the whole model. But there are a lot of buts in this process. We need to be cognizant of random or uncontrollable effects, and we need to be cognizant of where we might have less smooth parameter interactions where we need to do things a little bit more completely. So let's assume again that even in this kind of screening design level, we still have way too many things. There are way too many combinations for us to work with. We have too many parameters, we have too many levels. So we can start thinking about reducing the number of levels by reducing the size, the number of levels n, or reducing the number of parameters k. We can still run into millions of trials. So what we want to start thinking about is how we can parameterize those things. And when we run into constraints, we run into other statistical issues. So one of the common approaches to this is coding, where we code things down to 0 to 1 or -1, 0, 1, which can kind of numerically code for, we can numerically code for categorical variables. So if you've got variables that have, text values, you can use numerical coding for those. One of the problems with that is that depending on how you're doing optimization or how you're doing the analysis, your optimizer may assume that those categorical variables are evenly distributed or are sorted in a particular order, which could be absolutely wrong. I mean, I don't know why A comes before Z, except that A comes before Z. So there's no real reason why categorically coding those into numbers makes sense. So you can transform the parameter space into some easier way to think about this. Some software methodologies require that kind of approach, but again, you need to take some care that you're not actually making things worse rather than better by doing these kinds of things. Always, you should think about reducing the number of parameters. One of the biggest problems in machine learning research, we use a lot of machine learning models. A lot of machine learning papers come out of things like image analysis or text analysis, where you have relatively stationary data that's relatively similar, self-similar. Pictures of cats are pictures of cats, right? I can change the color, I can change the breed. It's still a picture of a cat. This is what we call stationary data. If your data isn't those things, then you're going to have problems with hundreds or thousands of parameters. So, but normally, what you can think about is which parameters are the most important. So you can do things like studies on parameter importance to try to get at ideas of how to get these things, to figure these things out. So what you find is that if you do small screening designs, you can find that if there are a large number of parameters up front. Need something, Justin?
Yeah. Pizza.
Okay.
Yes, the pizza intermission.
Pizza intermission. All right. So, anyway, so what we find is that most experiments with a large number of parameters have only a few parameters that have a large effect on the outcome. I think we're going to be fine. Okay. Our direct or main effects are more likely to be important than parameter interactions. We'll see this when we get to a larger example in just a minute. This is something that's known as the hierarchical ordering principle. So it's been known for a long time that if you've got hundreds of parameters or thousands of parameters, only a small number of them are actually likely to be significant, and only a small number of interactions are likely to be significant. So there are, of course, models where there are very small effects and you're trying to pick those up, but most models in the real world, especially on non-stationary data, have a small number of parameters that actually matter. There are approaches to do hierarchical experiment design. Bayesian designs come into this in many cases. They are definitely useful in some places. They're not terribly useful in my field of finance. If the number of parameters or interactions is really large, it can also be a reason to do hierarchical designs. But if it's widely used in your field, there are certainly processes for handling these. So we've thought about all this. We've taken out as many parameters as we can. We've reduced our number of levels. We still have too many combinations. So what can we do? Well, we can sharply constrain the number of levels and parameters even more than we already had. We can add more constraints, or we can get into what are called fractional factorial designs. So this includes things like random sampling. Latin hypercube designs are one way of doing random samples. You can use random design points within a range. For many years, I used uniform random samples, which can cover the area very well, but don't have a lot of statistical power. So if you want to simply cover the space, you can use a uniform random sample, but you may not have good statistical power because you may have missed turning points or inflection points in your data. Bayesian sampling is widely used when you have hierarchical models, and Fedorov designs. There it is in Cyrillic for those of you who speak Russian. I don't. One of the problems with this is actually that you'll find it spelled about 4 different ways in English. So in English, he spells it Fedorov, but most of the software implementations that I know of spell it Fedorov with an ER instead of an OR. So, but these designs we'll talk about more in a bit because they're important. So of fractional factorial designs, the random designs are easy, but they have low statistical power. They may not have good coverage of the space. They do have the advantage of incorporating complex constraints, which is why I started using them many years ago. Variants such as the Latin hypercube seek to improve that coverage. Most of the reference designs for Latin hypercubes are in Python. They seek to find at least one center random point inside each inflection set. So they're a way of kind of getting good coverage without covering the entire space. You can omit certain parameter combinations or ranges that might miss effects, which are more important. But hierarchical Bayesian models are very powerful, but they typically use multiple rounds of designs. So any design which takes the full brute force, which is called a full factorial design, and shrinks it down is called a fractional factorial. Now, in the types of models that I deal with, we tend to use algorithmic fractional factorial designs. The most powerful method here is the Fedorov designs. So a full factorial test covers all combinations. There are algorithms designed specifically for computational experiments, so thus useful to this group of people, that still maximize our coverage. So mathematically, this is known as what's d-optimal design, because you are trying to maximize the variance covariance coverage of the determinant of the multidimensional matrix. I decided not to put 3 or 4 slides of math up here to explain why that all works, but it seems to all work. People have been studying this for about 30 years, and they seem to work really well. The Fedorov algorithm maximizes that coverage by calculating support points in the multivariate ellipsoid space. So the math again is pretty complicated, but it works pretty well. If you have constraints, there's Monte Carlo versions of the Fedorov design that can get very close, like 98 to 99% de-optimal designs where there are still many parameters or very complex constraints. So for example, you've got this space and you cut off a whole corner of it. Well, now it's very hard to use traditional design models to cut off that corner. That's why people often resort to randomization. So let's take our original 3-level and 5-level examples where we had originally 243 and 3,125 rows. And let's take an algorithmic fractional Fedorov design here. So if we apply the Fedorov design to this, where we're using quadratic constraints and we're approximating to get to the final answer so that the code runs faster, you can go from 243 rows in the brute force to 202 rows in the brute force for the 3-level design. Not a big deal. You didn't get a whole lot of benefit there. But in the 5-level design, 5 things taken 5 levels for each one, we go from 3,000 levels to 230. And we still have over 99% statistical coverage of the whole space. So you can see how you've gained a significant amount of benefit by using a smaller design without having to go further than that. So let's quickly run through a larger example. So we've used 2 small examples to illustrate. We used the small example of the Bollinger Bands to illustrate parameter reactions, and we used the small examples of the 3-way and 5-way to demonstrate how an algorithmic design could decrease our search space. Design of experiments really is most useful when the total search space is huge or expensive. So in physical experiments, things are expensive because you can't change the machines that easily, or because it's really expensive to make mistakes on a production line, or because you only have so many patients in an actual live study in psychology or in medical research. Or in computational experiments, which I think this room and the people watching online are more likely to be, you have just so many possible combinations that it's expensive in terms of compute. It can cost thousands or even tens of thousands of dollars to run tests on a cloud. And maybe your boss says that that's too much money. So you want to do it in a faster period of time, or you don't want to break your laptop. Melting your laptop is a very real possibility. So let's examine an example that better approximates a real problem. It's still a toy example, but it's a large toy. So we talked about a Bollinger Band strategy, which is a band and midpoint strategy. It's very common in quantitative finance. Real strategies of this type tend to be significantly more complex than the one we examined earlier. So in this case, we're going to go from using 1 asset to using 9 assets, still not very many. And we're going to also add some more parameters. So we add 2 indicators. We configure it as an up and down trend with a breakout. None of that's super important. We have 4 rules for those of you who aren't in finance. But at the end of the day, we have 5 parameters and 3 constraints. So we've constrained these over relatively small ranges. So we've already smoothed things down. We've got constraints in here. With default parameters on a single core, this runs in under 30 seconds. So not super fast, not super slow. It consumes 80 degrees of freedom and retains over 99.8% of our total degrees of freedom. Now, if we do a broader range of these parameters, so we have our 4 parameters up top, we have the ranges here. So we have 5 parameters total with 2 set to be equal. We have 4 primary signals and 2 composite triggering signals. We have 4 rules, 4 parameter distributions, plus 1 equality constraint, and 3 additional parameter constraints. We now end up with over 100,000 combinations, still in a toy, right? This is a toy example. This is smaller than anything that you would do for real. If we increment all the parameter ranges except the standard deviation, which only ranges from 1 to 3, by 2 rather than incrementing by 1, we're now down to 20,000 parameters. So a lot, but that doesn't sound like a lot, right? We're in data science, right? 20,000 parameters doesn't sound like a lot. But we'll proceed with this smaller example anyway. To do this as a brute force example, on a 6-core, 12-thread, 64-gigabyte machine, this example will run out of RAM. It'll crash. It can't complete. On a relatively typical 8-core, 16-thread, 128 gigabyte of RAM workstation, The 20,000 parameter set brute force takes about 20 hours, running on all cores at 100%. On a 24 core, 48 thread, 256 gigabyte RAM server, which by the way would cost you about $150 a day on Amazon, roughly. The brute force parameter search takes about 6 hours. So this is still a toy. Real strategies with more parameters, more assets, more rules, higher frequency data, or all of those would obviously take much longer to analyze for real. So what's our impact on degrees of freedom? Are we overfitting? So if we look at this, we have 52,000 market observations over about 20 years of data. We use up 19,000 of those consumed by the strategy. Our total degrees of freedom remaining is 32,000. So we've used up 62% of, we have 62% of our degrees of freedom remaining. Ideally, you'd like to have 95% or more of our degrees of freedom remaining in a regression analysis. So we have a very high chance here of overfitting. And we've generously only considered 1 degree of freedom for each parameter test. If we use the most conservative counting, we'd end up with negative degrees of freedom. So we have a high chance statistically of overfitting by using the brute force example. So not only is it expensive to do this test, it's also likely to give us junk results. So let's go back to a fractional factorial design. Would this help? So an unconstrained Fedorov design returns about 900 parameter sets. So from 20,000 down to 900, that's a 95% reduction from our full factorial example. And it's a 99% reduction from the original increment by 1 design. When we apply constraints to the Fedorov design, there are 80 parameter sets remaining, which satisfy the constraints. So we've gone from 20,000 to 900 to 80 once we constrain it. This is a 99.9% reduction from our original set. It's a 99.5% reduction from the tested set. It's a 92% reduction from the full Fedorov design set. And our remaining degrees of freedom is 99.51% degrees of freedom remaining. So we have a much higher chance of a statistically valid result. And we've taken multiple orders of magnitude off of the computational complexity of testing this example. I'm going to come back to the parameter importance regression here. So again, this is a linear model. This is 1 line of code in R. It's a little more complicated to do linear models in Python, although we do them from time to time where we don't want to switch from one language to another. And we see that what we're doing is both, you can see the additive linear model, n fast plus n slow plus n sig plus n slow plus nd, SD. And we see also the interaction models with the asterisks between the effects. We use the same kind of net trading P&L and profit to max draw as objectives. Those aren't important for the purpose of understanding what we're doing here. When we look at the regressions here, what we see is interesting in that all the direct effects are significant. All of the upper ones have significance, or almost all of the upper ones have significance. The interactions are far less likely to be significant. So this is what I was talking about earlier when I talked about hierarchical ordering principles. As the number of parameters goes up, the likelihood that the interactions between the parameters are also significant goes down. So this was the regression that we just ran was run on that 80 parameter sets. It was run on the fractional Fedorov. So we were able to get statistically significant results from a regression model to look at how important our original parameters were based on this a test of 80 of these parameter combinations rather than a test of 20,000 parameter combinations or 100,000 parameter combinations. Instead of 20 hours on a fast multi-core server and relatively high chances of overfitting, a much more parsimonious design it runs in about 6 minutes on a workstation with a few cores. So that's a very reasonable time for you to think about, did I do this right? And can I learn anything from my model? We certainly run models that run for days. I'd rather not. I have some additional topics here. I'm going to kind of go quickly through them, but I know we're a little tight on time from what Justin was saying. Most texts on design of experiments spend a lot of time on randomization and replication methodologies. If you are doing physical experiments, randomization and replication help control for other factors that you haven't otherwise considered. So they're really important in the real world. They're not really important in computational studies. In most computational studies, randomization and replication aren't necessary. There are a few exceptions to that, but for the most part. Replication might be useful if the model contains a stochastic or probabilistic or other random component, because you need to make sure that it converges based on a whole variety of random or conditional calculations. But other than that, you shouldn't need to think about randomization for computational experiments. Split plot designs came out of agriculture because, in a big field, you don't necessarily know how much water is going to fall on each edge of the field or different elevations on different parts of the field. So you split it up into what are called split plots and try things in multiple different areas of the field. Again, very important in terms of physical experiments. So if you're doing physical experiments, you probably need to think about these things. Generally not important in computational experiment. All the conditions in your computational experiments are the same. So it shouldn't matter that much. Also, though, you need to remember that if you're doing analysis of variance, ANOVA statistics, you have to modify those for these sorts of split plot designs. So that standard statistical analysis for ANOVA doesn't work for split plot designs unless you modify it. Split plot designs, however, could be used for testing in production. So once you get beyond your computational test and you want to actually move into real testing, you may want to start thinking about this kind of design. Block designs are used to minimize average or nuisance factors when you've got variables with different inherent properties that are likely to affect the results. When you have noise factors that interact with each other, you do these block designs. Block designs make good sense in finance for things like asset classes, bonds, stocks, FX, crypto, all have different properties. So you may add blocks to a computational design. It doesn't make the design any more expensive to do. It's a different way of analyzing your results when it comes out the back. If all parameter combinations are tested on all blocks, you can use it to assess properties on a block by block basis, or you can do block designs where you make sure that you have standardized coverage across the blocks. Again, far more important in physical designs than in computational designs, but it can still be useful in computational designs if you've got other factors that you'd like answers for, but where you aren't going to vary them as parameters. Iterative sequencing of experiments. If you've got a really big problem, most of my problems are really big problems, which is why I've spent so many years thinking about this and now so much time over the last 9 months actually writing code to do this. It may make sense to iteratively sequence a set of experiments. Do small screening experiments, then do response surface experiments, then do parameter optimization across like larger numbers of levels for key parameters once you know which parameters are the most important, and then get into robust parameter designs. We'll talk about those in just a second. But the goal here would be to gain insight from each stage, correct your problems earlier on, and spend less time making mistakes. So if you're interested in noise or random or things that can cause problems in experiments, Taguchi is here. He's in the references. You can look him up later. But he identified different sets of noise. A lot of this comes out of the quality control literature. But it gets into what's called robust parameter design, where what we're trying to do is we're trying to identify parameters that minimize the overall impacts of as many noise factors as possible. Vary those factors that are controlled at design time. So the goal here is to try to have the most stable and robust parameters that you can. So out of sample in finance, what I care about is my parameters changing as little as possible, because if they change less, I'm less likely to overfit them. And you want to know when you need to change them because the environment has changed. So I often get asked about experiment designs for feature engineering. If you're trying to design an experiment to do feature engineering on a large machine learning model, most of the focus of design of experiments is on whole system outcomes. So it's about thinking about things that are already live production processes and thinking about how do I change things, how do I change my parameters to get better outcomes in production. Designed experiments can also be applied, they're usually applied late in the overall process flow. You already have a process and now you want to improve your parameter optimization. It's possible to use these techniques earlier, at the feature engineering stage. What you're generally changing is the target variables. If you're doing this on a production process, your objectives are going to be production objectives. You know, in my world, in finance, it's usually things like profit and loss. But when you do it in a feature engineering world, you're usually talking about things like goodness of fit or periodicity and persistence of the measured feature and prediction accuracy. So you can use these techniques on feature engineering as well. Anytime your feature has multiple parameters, you should be thinking about a designed experiment approach. Multi-objective optimization is a whole field unto itself, but many real problems have many objectives. Choosing the most robust out-of-sample parameters also requires taking these multiple objectives into account. One of the biggest challenges with many machine learning models is that they tend to be single objective models. So they tend to just look at things like gradient descent, for example, as their main objective. So multi-objective optimization can be an additive thing to this type of thing where we start looking at, combining or weighting the objectives, start improving our desirability functions, start treating objectives as hidden variables, or really using true multi-objective global solvers like NSGA3. Okay, Justin told me to go fast, so I went fast. I apologize. By the way, these slides are all compiled. The examples that I showed you were all compiled into the code. So there is code behind all of these things. We can make the code available. If anybody wants it, send me an email. I'm happy to give you the code for all of the examples. But what I want you to take away from this, design experiments can lower the size of your parameter space to be tested 3 or more orders of magnitude. Taking a problem from simply computationally infeasible or computationally very expensive to something you can do on an average sized workstation. It may still run out of RAM on a laptop because RAM is still a constraint, but generally speaking, computationally, you can handle it. The other really important point I think here is that proper design can result in more insight from your experiment, more inferential power. Boiling the ocean can easily lead to overfitting. It risks multiple testing bias. You can give up all of your degrees of freedom without paying attention to these things. The other thing is that rather than incrementally optimizing parameters, as many people do, you can simultaneously optimize all of your parameters in relatively small tests. It also provides a framework for iteratively more complex experiment designs. And finally, I think design of experiments is a tool that should be in every analyst's toolbox. It's more accessible than it seems in many ways. And if you take away nothing else, think about the fact of using Fedorov designs for algorithmically decreasing the number of possible parameter combinations. Some resources. I highly recommend the excellent Design and Analysis of Experiments by John Lawson. The Dean Voss and Dragulik book is also good for its breadth, and it has both SAS and R implementations. Python is actually harder. There are no single texts that I'm aware of. There is no book about design of experiments in Python that I'm aware of. The 2 best packages that I know are PyDOE and PyMoDOE. They're in the references at the end when we post the slides. The online book, Process Improvement Using Data by Kevin Dunn, does contain a chapter on design of experiments in Python. I think he uses PyDOE for most of his examples. The alg design package in R contains the algorithmic Fedorov fractional factorial design that I used in this presentation. And then the classic text on this by George Box and Hunter Sr. and Hunter Jr. Is Statistics for Experimenters. It's the best classic text. The first edition of that book, it came out in about 1980. It also includes really useful introductions to the core statistics. So I'm not a statistician. I was originally a physicist. Learning some of the statistics is actually incredibly useful. Box is probably the best of the examples for that. And at the end of this, there are a whole bunch of references. I think we have a few minutes before the alarms are going to go off, and we're going to be ended by that. I'd be happy to take any questions. Thank you very much.
Yeah, so as Brian just alluded to, in lessons in why you're nice to security guards and other support staff at a facility like this is because they inform me that we're about to have a fire alarm. So excellent for students studying for their finals right now. They decided to just do it now. So that's going to be at about 7 o'clock here. And what's going to happen is they're going to shut the elevators off. and you have to take the stairs like, you know, real fire alarm style. No, you can't. They will come and like clear all of this. So I suggest we kind of get a move on it here. Or I have walked the 12 flights a few times and it's not great. Now I will say that